Hi everyone, I hope you're doing fine. And in this video, I'll be giving introduction to FPGA and Verilog. And towards the end of the video, I'll be showing you how to write your first Verilog code in software called ISE. So what is FPGA? What does it stand for and what does it mean? And what is inside FPGA and how can we use it? How can we program it? Are the questions that we are going to solve to understand here in this video. So FPGA stands for Field Programmable Gate Arrays. So what is gate array? What is programmable? What is field here? So gate arrays. Are it's an array of gates or transistors that we use to make gates, to make any combinational circuit, any circuits that we want to do, we can make it using gate arrays. So this was what we had long time ago, like in history, long time ago. This is what we had, and after that, the problem with those they were fixed. You cannot change them once they are made. Once the metal is melted and the circuit is done using the gate arrays, using the transistors, they cannot be changed. So there was a need for programmable gate arrays. So we have to program them again and again, again and again. They should not be fixed. So programmable gate arrays came after that. After that, programmable gate arrays came after that. So they could be programmed, but still the problem with those were like only the factory make the programs. They can program it. No one else can program it. So once they are shipped into the owner, the buyers or the any low-level users, they cannot be changed. So they are programmed. They cannot be changed. So there was a need for programmability in the customer side, in the customer end. So the customer who bought the hardware has to be able to reprogram it. So that's what FPGA comes from. So the field programmable gate array comes from. Field means customers or users can program it. Okay, the customers can program it. So you buy an FPGA, you can change the hardware by making codes. You can make a hardware anytime you want. You can make CPU, you can make 7-segment driver circuit if you want. You can make any combinational circuit or sequential circuit. So this capability is given to the customer. That's why it's called field programmable gate arrays. Here, it's better to compare it with what we might know already, with CPU. So CPUs, knowing or without knowing, you're using CPU. So in every central processing unit, it's a processing unit which is found in every cell phones, laptops, or any smart things. There's CPU. Okay, CPU is central processing unit. So we will compare CPU with FPGA here. So CPU mostly it's fixed. Not mostly, but every time it's fixed. CPU is fixed size. So mostly it said like, so my laptop is, for example, 64-byte CPU. So the instructions that it does or the inputs or outputs that it takes is 64-byte based. So it's fixed. I cannot change it. So it's fixed. So FPGAs, they can be configurable. So I can make CPUs in FPGA if I want to. So in other courses that I'm an assistant of, so we do CPUs using FPGA. So the CPU, I can make it small CPU or big CPU, any circuit that I want, I can make it on FPGA. So it's configurable. I can change the FPGA circuit that I did inside the FPGA. I can change it anytime. But CPU, it's fixed. By itself, it's fixed. I can only change the programs that run on the CPU, the softwares, not hardware. Hardware in CPU is fixed. Here the hardware can be changed anytime you want. And the other thing to compare with is low executable speed. So CPUs, because they do things sequentially or in order, one by one, step by step, that's why it's very slow compared to FPGAs. But FPGAs, they're fast because they do things parallelly. So they can have, for example, I can have in my FPGA, if my FPGA is big enough, I can have 3 or 4 CPUs side by side working in in parallel. I can make them work like that. So this is one advantage of it, and the other advantage is which is portability of design. So if I have design, it's very easy to adapt it into different FPGAs compared to CPU, because CPU is already fixed. So that's another advantage of it. So if we were doing our lab in the school, in our labs, this was the FPGA board that we were going to use. So it's called FPGA Digilant Basis 2, and this is the board of the name of the board is Basis 2, and the FPGA we have is on the center of the board. This is actually the FPGA. These are just 7 segments, switches. We have here, these are push buttons, and we have switches here. We have LEDs here. We have power button here, power switch here, VGA and all that. VGA, which is connected to monitor, and we have USBs here. We have Ethernet cable that we can put. We have pin here. So these are what we had, but this is the one that is called FPGA. Like, this is the board and this is the FPGA. So this is the FPGA. When you look closer a little bit, this is how it is called. It's an IC. It's an integrated circuit. And let's look much closer. So we're going to look inside of this FPGA. Inside of this, what do we have inside? So inside the FPGA, we have 3 things, 3 categories of things. So the first one is input and outputs. All the things that you see on the sides are input and output blocks. So they can be, so one of these, for example, I can set it as an input, or I think I can set it as an output, or I can use it as input output. So these are just input output blocks. Okay, the second one is logic blocks. They are called configurable logic blocks, CLBs. So they can be, these are the squares that you see everywhere are they are composed of LUTs. I will come up in the next slide, but they are configurable logic blocks. So they can be changed anytime I want, according to my program. Okay, and these are actually the ones that are doing the decisions. These are actually the mind of the FPGA. These are doing the decisions, and the calculation and everything is done inside the configurable logic blocks. And the other thing is interconnections, programmable interconnections. So the interconnections are also programmable. So the connections, I can remove this connection and make this connection. So the interconnections are also programmable. That's the advantage of it. That's what makes it highly. It makes everything possible. That's the main reason of it. Okay. So 3 parts we have here, and let's look closer to the logic block. Yeah, there's interconnections here. We can see them here. So sometimes my design can be finished, right? It can be enough. I mean, only one CLU, I mean LUT can be enough for it. So I can do it in only one logic block. I can do it in only one logic block. If my design is small, it can be done in that. But sometimes I have bigger inputs, a lot of inputs and a lot of outputs, and I have to use many of the LUTs to make the design. So that's why we need the interconnections to make connections between designs, between the blocks. So FPGA is sometimes measured by its number of LUTs that it has. So our FPGA that we are using is using, it has like 74,000, more than 74,000 LUTs inside it. So the more LUTs I have, the bigger the circuit I can make in my FPGA. And yeah, and the more expensive it is. So for example, I want to make a gate. So it could be more complicated, but just for explanation purpose here, I used a simpler gate. So this is AND gate, and I want to make AND gate in my FPGA. But in FPGA, I have LUTs. I don't have AND gate. I have LUTs. LUT is lookup table, by the way. It's a lookup table. It's a table that is composed of input and output. And for any inputs, I have outputs. So I can describe the gate or any combinational logic or any circuit that I have with LUTs. This is the behavior. This is describing what this is. My design, I write my code here. It's synthesized. The synthesis gives us this. The synthesis output gives us the LUT, the behavior of it. And this is saved inside the FPGA, inside the LUT. So for any input, there's output. So you just have to provide inputs. It will give you outputs. So it's kind of imitating what the hardware is doing, what the actual hardware is doing. But inside the hardware, we have this, but this is actually what we had in mind, and the synthesizer changed what we have written into a thing that FPGA can understand, which is LUT. So the LUT is saved inside, yes, this is the table, a truth table, by the way. It's a truth table. So this truth table is saved inside the LUT part. So whenever input comes, I get the output immediately. Okay. So in this format, we can put any designs, any combinational circuits or any sequential circuit that we have, and describe them with our code. The synthesizer will convert them into LUT blocks. It could be a lot of LUT blocks. It could use a lot of LUT blocks and gives us the output according to the description that's given in our code. And the LUT blocks that we have mostly they have 2 inputs and 1 output. Sometimes they have 3 inputs and 1 output. The most I heard so far is like 4 inputs and 1 output. So if I have 16 inputs and 1 output, I have to use combination of like 2 LUTs or 3 LUTs, 4 LUTs, something like that. I have to combine all of them. Okay. And what is Verilog here? So what does Verilog mean in terms of in FPGA? So Verilog is a hardware description language. So as a language that describes a hardware, not a software. It describes a hardware. It describes a circuit. Okay. And for that, for hardware description, there are a lot of so the ones I know and the ones that are actually are VHDL and Verilog. And VHDL, I know how to use it, but like we don't use it here. Verilog is the one we are using here. And once you know Verilog, it's very easy to adapt into VHDL. They are basically similar, and we use Verilog in this lab. So Verilog is used to program FPGA. So we have FPGA, we program it to make a circuit, and that program that we use is Verilog here in our lab. It's also VHDL is also used, but here Verilog we are using. And if we say, this is very important, if we say compiler for a software, we say synthesizer for a hardware. That means Verilog is not compiled, it is synthesized. Okay, it's synthesized. Synthesis output will give us LUTs. It will match it into our FPGA, whatever FPGA we have, how many LUTs we have, it will match it into that one. Okay, so but compilers are just maybe you know it from C++, from Java, or from any Python. when you compile it, we use compiler for that. We compile it, and then the compiled version, which is assembly and machine language, is given into the CPU. In CPU, it's executed line by line, instruction by instruction. It's executed in that way. But here, synthesizer is the way to go. We use synthesizer to convert our description, our hardware description, Verilog language, into a hardware that FPGA understands. So this is our first. Let's go to our first design. So this is the circuit we have here. So in the circuit is shown like this: A and B or C is equals to Y. So Y gives us whatever the inputs are coming here, they pass through the gates and then gives us output. This is the normal way that we do in the lab. So I give a name for that to design it in Verilog. I give a name which is combi circuit.v, combinational circuit.v. This is my design, and I want to design this in Verilog. So there are two ways of doing it. I will show you both of them in the demonstration of writing Verilog in ISC software. So the first one is just by looking at what the gates are there, we just copy what is shown there. For example, we do A and B or C. This is a structural way of doing it. It's called structural way of doing it. We just do A and B or C. We use AND operator, we use OR operator, and we equate it into Y. That is one way of doing it. That's called structural. And the other way of doing it is behavioral. So if I know the behavior of this, if I know whenever I give it 0, 0, it gives me 0. Whenever I give it 1, 1, 1, it gives me 1. Whenever I give it different inputs, if I know all the outputs, then I don't need to know what's inside. I just know the behavior. So I can make a truth table out of it. And I can transfer that truth table into my codes, into Verilog code. Say like if 0, 0, 0, Y is 0. If A is 1, B is 2, B is 1, and C is 1, Y is also 1. I can say like that. The behavior can be written in that way also. Okay? There are two ways of doing it. I will show you both of them. After we have designed our design, we have to simulate it. Where are we simulating it? Where are we simulating it? We need simulation because we have to check if our module, if our circuit is working correctly or not before loading it into the FPGA. We don't, because we are doing this in online, we don't load it, but normally in design flow, when you design, you have to design your circuit and then pass it through a test bench. You have to give it inputs and expect output. If you don't get the expected output, then the design has to be revised again. And that's the way to go. But here we have to show it using the simulation. We have to see the waveforms through time. At this time, I gave it this input, I'm expecting this output. Next time, after 50 nanosecond, I give it this input and expect this output. You can do like that. So I will show you how to do this in a ISC program. Let me pass to that. Yeah, here one other thing is that we have to always remember that we are designing hardware. We are designing hardware, not software. We are designing a circuit, just like we do it in the lab using components. We are designing a hardware here because sometimes it's confusing because you are writing code. You might think you are writing software, but not. It's not software, it's a hardware. We are designing a circuit. Okay, so let's design our circuit using ISC. This is ISC program. I'm starting it, and let's start from here, new project. Let's give it a name, tutorial 1. It's tutorial 1, and everything here has to be same, by the way. Every family names has to be Spartan E, and device has to be like this, same 100E, and here it has to be CP132. Why are we doing this? Because our design has to target one FPGA, because that FPGA has different number of LUTs. If it is big, then it has bigger number of LUTs, so we have to think of that. So if it is different, then it's a problem, because your design might not be appropriate to the FPGA. And next is everything has to be similar. Verilog, it has to be selected Verilog, and it has to be iSim simulator, and synthesis tool has to be VHDL Verilog synthesizer, and everything is as default, and say next. Like, once you have to set it like this, maybe yours will be different from here, but you have to set it exactly like this. Once you set it, next time when you open it, it will be the same, no problem after that. Mine is set already, and it's all okay. You can set it from here. Okay, next, we finish. And then, so this has to look in the same manner. It has to look like this for CP132. It has to be like this. And let's create a new Verilog module. Here, select Verilog module and give it a name. What's the name I'm gonna give it? It's combi circuit okay, combi circuit.v. .v, it means if I selected Verilog, there's no need to write .v here. .v, so we just say next. Here I don't need to set inputs, just say next. Same thing here, finish. So afterwards, I will write my code here. I can clean this one, and do not clean this part, only the inner part will be cleaned. So this part has to stay there, it's for simulation purpose. If you don't have it, then it will be a problem. Next. So what do I have? I have inputs here. I will try. So module, it's the keyword, it's also a keyword here. This is, you don't change this. Module, int module, they are together. And here I can give any name here, but it has to be the same. I gave a name, same thing, but it came similar here. So combi circuit is the name. So I'll list all the inputs and output ports here. Okay, my ports were from here. What were my ports? It was A, B, C, and Y. Let's go to A, B, C, and Y. A, B, C, and Y. So I don't need to tell them here what it is, whether it is an input or output. I just say they are ports, input and output ports. Here I will say input. They are here, A, and I will do the same for B. I can do the same for B and C, but you can also do something like this, B, C. It's fine. It's fine like this also, okay? Next is output. My output is Y, okay? Now I have it like this. So just like I told you, there are two ways of doing it. So I'm gonna do the structural version of it. What is the structural version? There was AND gate, there was OR gate, yeah. So I can just say assign Y equals A and B. After that, or C. That's it. This is what we had, yeah. After that, we just go. This is an implementation part, by the way. We just go and synthesize here. Run. Save and run. Synthesize might take a while if the design is really big. So now we have synthesized it already. So this is our synthesize, and next we have to simulate it. Yeah, we have to see whether it works correct or not. We have no error here, but let me show you one error. Let's say we don't have this here, and save it, and when I synthesize it I see an error, and I just go to the first one, the first error, click on it, it shows me here. What does it say? Unexpected token C. So there's a problem around here in this line, which is this point. Line 9 is also saying, line 9 nothing. So if you fix one of them, mostly it's correct. So it could be caused by the first problem, so you just have to fix one of the first one and then run it, but fix the top one, and then you have it here. And then let's write the simulation part. Okay, so for the simulation part we have to create a new module. It's also Verilog module, but this time it's a test bench. Test bench is a Verilog file which is used to test the Verilog module that you have, that to test your design. Okay, it's a different Verilog file. So let's write combi. It's just the naming is just a format. It's a lot better to write it like this: test bench tb combi circuit. Okay, combi cb circuit. Next, that doesn't have inputs. So here I have already written the, so I'm gonna clear this. Okay, so as you can see, it doesn't have inputs because it doesn't have inputs. Test bench doesn't have inputs. I mean, it doesn't have to give inputs, so it just tests our circuits. I'm gonna show you step by step everything that you need to know. So test bench, as we know, it has, the test bench doesn't have inputs, doesn't have outputs, so it has some kind of variables, and those variables are given into A, B, and C, and Y is also a variable there. Okay, and let's see. Here we have variables called A, B, C. So if you give them different names, so this has to be different, this has to be different. So if I say this is V, and this also has to be V. Okay, but for now let's stay with A. Mostly making it similar is better. So this is the register. Register is a variable. It's just a variable. Okay, it's inner variable inside the module. It's not outside the module. Inside the module we have a variable. Okay, after that this is also a wire. Wire is just it's an output. Wire is just like a register. For now, just consider wire as a register. When the time comes, we will explain what it is, but for now it's a wire. And here, because I'm giving inputs to this one, that's why it's called register. Then the values change here. I'm gonna give values here: A, B, C, D, A, B, C. I'm gonna give values. That's why Y is just an output, so that's why I give wire here. So this is my module. Here it's called instantiation. It's like calling a function kind of. Okay, it's connecting my test bench with it's connecting my test bench with my design. Here is the connection. If I delete this thing, there's no connection between this module and my design. So this is how it's there. So the name has to be the design's name. I can give any name here, but here unit under test, I give it unit under test. Sometimes it's called DUT, device under test. I have given a name like that. After that, so this is the place where I give inputs: initial, begin, until end. Okay, so here what I have done is I have given values to the inputs. So I'm giving inputs into my design, my testing design. So I give inputs 0 0 0 0, okay, and I wait for this much time. This is nanosecond, okay, 50 nanoseconds because of this. Okay, 50 nanoseconds I wait, and then give another input. I just give another input, and I'm gonna see the output in the waveform. I'm gonna check the output. So when I give this input, what is the output? When I give this input, what is the output? When I give another input, what's the output? So I can try all of them, but for now I just put a couple of examples, couple of combination of examples. So I give this and then wait for a couple of time and then finish. Okay, I can say finish here, and everything finishes here. So what happens? So let's run it. But before that, one thing you should always remember is that we have in implementation form. In implementation, we can synthesize in implementation. Okay, synthesizing in implementation is possible, but we have, when we go to simulation, so they are not inside. So there's a problem here. So I will go here to this file and go down to source properties, option source properties. When you go to source properties, you have to select simulation here and apply, okay, and okay. So now we don't see the test bench in implementation, but when we go to simulation, we see both of them, test bench and combination, but they are just side by side right now. I will save this part. When I save it, I saved it. When I save it, it's like this. So this is inside the test bench. So this is the format that we want to see. Okay, now we will run our test bench. How do we run our test bench? Select the test bench first. Do not select this one. Select the test bench. Make sure it is under simulation. After that, go here and then run all. Simulation behavioral model, run all. When you run it all, there will be a new window coming. This window will be coming here. But if you don't see any window coming, then in installation there is installation problem. You will see a problem here maybe, or maybe you'll see error in here. That time you have to go back to the installation and then see the file of installation, and maybe you can send us email also. We can help you with that. Okay. Now let's go to another the second module, which is the second window, which is the simulation window. So after simulating it, we have seen it's at finish part, and we can see the default.wcfg. The waveforms are seen here. Okay, as we see, click on here and plus minus minus. When you press minus minus, you will see the waveforms changing. So what do we see here? So we have output Y, A, B, C. So the inputs are changing. Let's say this one is changing to a 0 and it was 1 again, and it's changing. So I will see the output. Let's make it here. Y is here, and let's drill down. There's no need to save anything. Okay, let's go back to default file, and let's see what we are doing. Let's check if our design is working right or not. So according to our design, whenever C is 1, output has to be 1, yeah? Whenever C is 1, output has to be 1. So at this time, it was a 0 second. The inputs were 0 0 0. You can see the inputs 0 0 0 0. So output is also 0. Output is also 0. Okay. At 50 nanosecond, 50 nanosecond. After 50 nanosecond, what happened? The input changed. 0 0 1. A, B, C became 0 0 1. So output has to be 1. Why? Because C was influencing a lot here. Whenever C is 1, it makes the whole thing 1. Yeah? So that's the case. and sorry here. So when okay, after 15 nanosecond again, the input changes, it becomes 1 0 0. So A and B is 0, we have 0, so it will be 0. Output is what? Output is 0. Okay, next we see the inputs are, we have to see here, the inputs are 1 1 0. So A and B is 1, and or C, 1 or C is 1, so the output is 1. So we have it here. So this is how we check it. So there are other things that we can do is because these are 1 bit, there's no need to do, but you can change the radix of this, which is, where is this radix? It's 1, so there's no need for that. Okay, so this is how you show the output, and this is what is expected from you. So this is how you test your module, and as you can see, test bench, there's device under test, and these ones are inside our module, and we can see our output in this way. Okay, the other way of doing it is here. Okay, so now we have the second way of doing it, the second way of designing our circuit, which is behavioral circuit. The one before this was structural, just looking at the AND gate and OR gate, but here we have behavioral. So we're just showing the behavior, how it behaves. If something happens, then the output is this. If input is like this, then the output is, that's what's called behavior. Okay, just like truth table kind of. Okay, so we have changed things here. For behavioral, we have to put always at begin here. So this is just a block which works in parallel. So if I have more of this here, if I have more of this here, two of these blocks, then this block and that block work in parallel. They are independent of each other. Okay, and that's why it's a small block of it. Okay, now let's go back. Okay, so in this section we have changed this part, which is reg. So this is the Verilog part, not the test bench. The test bench, I didn't change anything. The test bench is similar, it stays there. But the Verilog part, I have changed it into a different behavioral form of it. So here we have A, B, C, the inputs are same thing. I didn't change anything, but here I have changed Y to reg. It's output and it's a reg. Earlier I didn't write anything, so by default, if you don't write anything, it will be considered as wire, but here it's a reg, because I'm going to put it inside always block. Inside always block, I have to put reg, so anything on the left side has to be declared as reg here. So what is happening here? So whenever I say here inside this block, if C is 1, it's the same like this. If C is 1, Y is 1. That's how our circuit was behaving. Yeah, if C is 1, Y is 1. It doesn't depend on A and B. Okay, otherwise if A and B are 1, then it doesn't care about C, it will be 1. A and B are 1, then it will be 1. So I know the behavior, so I'm just gonna write how it behaves. So if C is 1, then Y is 1, else if A is 1 and B is 1, then Y is 1, otherwise Y is 0. So this is the behavior of it. Okay, and let's save it and let's run. Let's simulate again. I have to close this part. Okay, let me write it again, because if it was open, then running it while it was open it gives error. Now I'm running it again. Rerun all. So let's see here. Let's make it smaller so we can see minus minus. Same thing we can see here. 0 0 0 1 0 0 1 The output is here, it's 1. When C is 1, it's 1, and the behavior looks like this, and they are having similar properties. So I showed you two different things of designing circuits, which is combinational circuit. And for this introduction, this is how it is. And starting from the next lab, we will start doing sequential circuits on Verilog. But for introduction, this is combinational circuits on Verilog. And I will put this slide on LMS, and there are some links here. You can see these links, YouTube Verilog tutorial. This is a good one. You can follow it. And this chapter, this is one chapter of a book, and it describes all about Verilog that you need to know. And most of Verilog related questions come from here. If we had, maybe we will have some quizzes, or maybe homeworks, or maybe pre-labs for sure. They will come from this book. Okay. Thanks for watching.